Zeno's arrow hangs suspended in the air. In the ancient philosophical paradox, an arrow in flight must occupy a specific space at any specific instant. If it occupies a specific space, it is motionless. If time is just a collection of these motionless instants, motion itself is an impossibility. Classical physics dismissed this riddle with the smooth continuity of calculus, but the quantum world, the bedrock of our reality, has dragged it back from the grave with a vengeance. In the subatomic realm, the arrow really does stop if you stare at it hard enough. In 1977, physicists Baidyanath Misra and George Sudarshan peered into the mathematics of quantum evolution and discovered a terrifying implication. They called it the Quantum Zeno Effect. The logic is rooted in the collapse of the wavefunction. A quantum system doesn't exist in a single state. It evolves through a probabilistic haze, a superposition of becoming something else. But when you measure it, you force the universe to make a decision. The wavefunction collapses. The system creates a definite now. Misra and Sudarshan realized that if you force this decision fast enough, if you measure the system repeatedly with zero interval between observations, the system never has time to evolve. It gets reset to the starting line over and over again, trapped in a single moment of existence forever. For decades, this was a subtle ghost in the data, seen mostly in the decay rates of unstable particles. But in 2025, the game changed. A research team led by Zhang didn't just slow down decay, they froze the spatial reality of a single atom. Using a deeply precise optical dipole trap, they isolated an atom whose natural inclination is to spread out. A quantum particle left alone acts like a gas, its probability cloud expanding into the void. But Zhang's team bombarded it with measurements. They didn't touch it with matter, they touched it with information. The results were stark. Under the stroboscopic glare of rapid observation, the atom's diffusion halted. The probability cloud could not expand. The kinetic energy that should have carried it across the trap was nullified, not by a physical wall, but by the collapse of the wavefunction itself. This is the 2025 frozen atom anomaly. It confirms that time, or what we perceive as the flow of events, is not an absolute river. It is a fragile sequence of states that requires unobserved privacy to flow. When we strip away that privacy, when we become the relentless witness, we jam the gears of reality. The atom remains locked in its cage, not because of a force field, but because the laws of physics forbid it from changing while it is being watched.
From this paralysis of time emerges a new kind of control. If we can stop a quantum system from changing, we can stop it from dying. The paradox of the frozen arrow is transitioning into the era of the guided missile. The narrative of 2025 isn't just about stopping atoms, it is about measurement-induced directional transport. This is a phrase that should make every engineer sit up and take notice. Zhang's team discovered that by breaking the symmetry of their observations, by measuring the atom in a specific spatial sequence, they could force it to move without imparting physical momentum. Think of it as teleporting the probability distribution. Instead of pushing the atom, they collapsed it here, then collapsed it slightly to the left, then slightly further. They guided the particle across space using nothing but the Zeno effect. This is the birth of motional-state engineering, a field that treats the wave function not as a description of nature, but as a handle we can grab. And the killer app for this technology sits at the heart of the 21st century's most difficult challenge, the quantum computer. The great enemy of quantum computing is decoherence. A qubit needs to maintain a delicate superposition of 0 and 1 to perform its miracles. But the chaotic noise of the universe, thermal vibrations, electromagnetic whispers, acts as a clumsy observer. It measures the qubit randomly, collapsing the superposition and destroying the data. The computer crashes because the universe looked at it. The Zeno effect offers a shield. By implementing a protocol of rapid, controlled measurements, xenoprotection pulses, we can force the qubit to reset to its coherent state faster than the environment can ruin it. We are essentially staring the errors out of existence. If the qubit tries to drift into a decohered state, our measurement slams it back to purity. This concept suggests that the key to the next generation of computing isn't just isolation, it is active, aggressive observation. We can grant our data a form of immortality, freezing its integrity against the entropy of time. We aren't just observing the universe anymore, we are hacking its refresh rate to build the ultimate machine, proving that in the quantum world, the observer is the most powerful force of all.